invited me at this nice conference in this wonderful place, which I always enjoy whenever I come. So this talk is based on a recent work. Do you hear me? Yeah. Okay. Which is done in collaboration with Tommaso Aste and Massimo Picachamarra. The main idea is to try to find a connection, if there is, between glass transition and the jamming transition. This is an old problem, an old question, which always was considered in a seminal paper by Leo and Nagel in 1998, who proposed a universal jamming phase diagram in order to unify the transition from a fluid to an amorphous solid, which is common to different systems, including the glass and jamming transition. However, more recently, a distinction between the glass transition and the jamming transition came out in an analytical study of frictionless hard spheres in the infinite dimensional limit. And one of the people who is responsible for this is here, is our chairman. So in this talk, I will present results which are based on a combination of a cell theory for liquids and random first-order transition, which, as you already have heard this morning, it was developed by these three people, Schematic, Tirumala, and Borines, who suggest that in finite dimensions, in frictionless hard spheres, jamming and the glass transition may coincide. So let me first say a few words on glass transition, in particular on RFEOT, the random first-order transition. So as you know, when a liquid is supercooled below the melting transition, it may enter a regime which is characterized by very slow dynamics with diverging relaxation time, which is followed by structural arrest. One of the first theory which was proposed by Gates and collaborators was the mode coupling theory, who proposed a theory for the glass transition which is based on some approximation that nowadays we understand is some sort of mean field approximation. This mode coupling theory makes a number of precise dynamical predictions, and in particular, it was found a glass transition temperature, Tc, where the relaxation time diverges as a power law. So tau goes at T minus Tc to the minus gamma. And as you know, experimentally, this relaxation times appears, the relaxation time appears to follow a different type of law, and mainly an exponential type of law. At the same time, these three people, Kirkpatrick, Tirumala, and Borines, proposed a different scenario. No, not a different, so different, but a more complex scenario, which goes as the name of random first-order transition. And this scenario was proposed for both mean field and finite dimensions. So in mean field, based on the P-spin model, as you have heard this morning, the RFEOT scenario suggests first a dynamical transition at the temperature Tc with the same dynamical behavior of mode coupling theory. But then below this critical temperature, they propose a static transition, Tk, where the configurational entropy vanishes, which corresponds, to, if you like, to the so-called Kautzmann transition, where the entropy vanishes. So this is more or less the situation for mean field in the mean field theory. In finite dimensions, random first-order transition is modified and predicts, in fact, that mode coupling theory, dynamical transition, in fact, is smoothed and becomes just a crossover towards the static transition which occurs at a lower temperature, Tk. And this static transition is called the ideal glass transition. So one of the main ingredients of this random first-order transition in finite dimension is that close to the glass transition, the decay towards equilibrium is due to a cooperative rearrangement of a region of, if you like, of droplets of linear dimension xi, and this xi diverges as you approach the ideal glass transition. These droplets play the role of nucleating droplets in a third-order transition, except that here, due to the disorder, the droplets are in different glassy states, as opposed to what happens in a normal, in a non-disordered first-order transition. That's why this is called random first-order transition. Like in ordinary first-order transition, the free energy of a nucleating droplet contains, as you know, a volume term plus a surface term. Within the RFOT, the surface term is modified into a term which is proportional to xi to the theta, instead of being xi to the d minus 1, with theta equals to d over 2. This is not accepted by everybody, but they gave an argument for which theta should be equals to d over 2. D being the space dimension. So with this ingredient, and by developing this kind of theory, at the end they predict that at the ideal glass transition at Tk, the psi diverge with an exponent nu equals to 2 over d. The configurational entropy goes to 0, is related to psi by this relation. It goes to 0 as t minus tk according to the Katzmann suggestion. And eventually the relaxation time diverged with an exponential type of law, which is the so-called Vogel-Fuchs-Tammann law, which is more closely related to what is found experimentally. So what I've said is just has to do with the glass transition. Now, what about the jamming transition? You know that when a system jams, it goes from a flowing to a rigid state. In particular, just to fix the ideas, for a system of hard frictionless particles, if you increase the external pressure, P, the volume fraction increases. And as the pressure tends to infinity, the system reaches a jamming threshold phi j, where the coordination number zeta jumps from 0 to its isostatic value zeta chi, which is equals to 2d, d being the dimensionality. This isostatic value is a condition for the system to be able to satisfy the mechanical equilibrium conditions. So from this phenomenology, you understand that the transition is a kind of first-order transition, because zeta goes from 0, jumps from 0 to a value equals to d. However, there is also a critical behavior, more typical of the second-order transition, of continuous transition, which can be described by different exponent. One is this delta R square, which is the so-called cage order parameter, where delta R essentially is the linear dimension of the cage in which there is the jam of the particle. And as you reach the critical threshold, this quantity goes to zero according to this law, to this power law. At the same time, the pair correlation function at the jamming transition behaves as r minus sigma to the minus gamma, where sigma is the diameter. So what you understand from this type of critical behavior is that there is suddenly some sort of jammed state where a macroscopic number of particles starts to touch each other and form this jammed configuration. So these are just two of the many critical exponents which can be introduced to describe the jamming transition, which satisfy scaling relation, has been described very nicely by De Giulio, Lerne, Brito, Weart some time ago, and also other people, of course. So this is the jamming transition. Now, if we want to study glass and the jamming, one way is to study a frictionless of hard spheres, a frictionless of hard sphere system. And in fact, such a system has been studied by many people, including our chairman. And in this way, they managed to study both the glass transition and the jamming transition. So what they found, essentially, this is a schematic phase diagram, which I have adapted from a paper of Cauchan and co-workers, where you have here 1 over P, where P is the pressure, and here is the density of spheres. And when P is small, you are in a liquid state, and this continuous line is an equilibrium line. And as you reach this density, rho d, you reach the dynamical transition that we already seen in beam field. And later on, at higher pressure, you find this ideal glass transition according to the scenario of the random first order transition. There is a first dynamical transition, and then there is the ideal gas transition. Here there is something else, because there is a glassy line now which connects the ideal glass transition with the jamming transition. And here are also indicated with a dashed line the out of equilibrium compression protocols that takes you from one of these point to, when P is infinity, to the jamming transition. So there is a jamming line ending on this line, this point here, which is which is on this equilibrium line. What is also interesting that these people, always including our chairman, they calculated the jamming critical exponents analytically using a replica theory for hard spheres in the limit of infinite dimensionality. And the amazing result is, I was very impressed, I must say, by this work, because the amazing result is that these exponents, which are calculated in beam field, or if you like, in infinite dimensionality, are in excellent agreement with the numerical results in d equals 2, 3, and even more dimensions, and so seems to be universal exponent, independent on dimensionality. In fact, Nagel and co-workers already noticed this feature, and in fact, they even proposed that maybe in this jamming critical problem, the upper critical dimensionality is 2, so that from d larger than 2, you will always get the same exponent, as is found, in fact, in the infinite limit d equals infinity. So you can imagine, you solve the problem in d equals infinity, mean field, that you don't have to do any epsilon expansion, nothing. You just get the right result. I'm really impressed, really. So now the question is, so far so good for the critical exponent. The question now one can ask is, what happened to this phase diagram in finite dimension? We know already that the dynamical transition is mooted when you go to finite dimension. So the question is now, oh shit, you don't say that. Oh, this goes into now, oh my God. It's gone already. Okay. I have to put this one. So this is, okay. So the question is, what happens to this phase diagram? So in particular, what happens to rho k? If we go to finite dimension, can we expect that rho k is different from rho j, or maybe rho k may just go and becomes identical to rho j? This is the question that we try to answer. So now comes the part which we studied essentially in finite dimension. This work done first with Tommaso Asta and later also with Massimo Picachamarra. We start essentially from first principle and apply statistical mechanics formulation for a hard sphere system. So the partition function is essentially given by this multiple integral, as you know. And for hard spheres, this U is the hard sphere potential. Now, the cell theory is, the first step of the cell theory is to divide the entire volume in cells, and the cells are built around the particle's position. Then the integral for each particle can be divided in a sum of the integral over single cells. So each of these integral becomes a sum over all these cells. What are these cells? These cells essentially corresponds to Voronoi tessellation. So this is an example or a configuration of hard spheres which has been divided in so many cells. So each sphere now is characterized by a free volume V. This free volume is defined as the volume where the center of the spheres can translate, given that all the other particles are fixed. So you can imagine when the free volume is 0, that particle is a jumped particle, essentially. So when the free volume would be 0, on average, that would correspond to a jumped transition. Now, elaborating such a theory, eventually one reaches this expression for the free energy, where P of V is the free volume distribution. And this free volume distribution is a so-called gamma distribution, contains this parameter K. This parameter K, if K equals 2, gives back the free volume distribution of the free volume theory, essentially. But by introducing in a way, introducing the static length of the random first order transition in a way that I'm not explaining here, but in quite a natural way, then the free volume distribution will contain this K, which depends on psi, the dynamical length of the RFEOT theory. So the dynamical length diverges at rho K with this exponent 2 over D, and this is S of C, which comes naturally, as it goes to 0 at rho k in this way, exactly as happens in random first order transition. Just to see that everything is quite coherent. Of course, I did not give you the details, otherwise I don't think I would have enough time. And this free volume distribution has been also found by Aste and Di Matteo in not only numerically generated sphere packets, but also in real parkings for different density. And they follow, in fact, this gamma distribution. So from the free energy, one can get the equation of state. And the equation of state, I take a derivative of log z of beta to v, and the equation of state gives this expression. So you can see that the pressure diverges when V reaches this Vj. Vj is related to the jamming density in this way. So this equation of state predicts some sort of jamming transition at P infinity. And now we have to understand whether the length psi diverges at rho k, where rho k is smaller than rho j, or whether it diverges at rho j, this jamming transition. So this is the question that we have to understand. And the answer comes from the free volume distribution, because this free volume distribution, the one I showed you before, has the property that when k, the k that appears, which is related to psi, when the k goes to infinity, means when psi goes to infinity, the free volume distribution becomes a delta function. And this delta function characterizes, in fact, the jamming transition. So where rho k, where psi diverges, must coincide with rho j, the jamming transition. And therefore, we expect that the length psi, which is related to the random first order transition, diverges at rho j with this exponent, 2 over d. So there is a prediction, if random first order transition is correct, if it gives the right result, there is a prediction for the jamming transition, because at the jamming we should find this kind of diverging length exponent. And in fact, we have done numerical simulation for soft spheres at t equals 0, which is equivalent to the simulation for hard spheres, by looking at the distribution of the jamming threshold. And the distribution of jamming threshold, in fact, it is related to the exponent 1 over nu. So phi j of n is the jamming threshold for finite number of particles n. Phi j infinity is for n infinity. And this difference should scale as n to the minus 1 over d nu. And what we find that for d equals 2 and d equals 3, we get always the same result, n to the minus 0.5. So if you put 1 over d nu equals to 0.5, you get nu equals to d. So this is somehow confirms that the theory which predicts that at the jamming there should be a length which diverges with exponent 2 over d, this is found at least numerically. And we've done this in using 2 different methods. So schematic, so the phase diagram, this is the phase diagram in mean field or infinite dimensionality. And so what we suggest here, that the phase diagram should have this line, equilibrium line, which ends at density rho k, which coincides with rho j. So this, the end of this line is ends at a point which is both a glass transition, the ideal glass transition, and the jamming transition. Okay, so now if we want to understand, if we want to understand that what is the critical behavior now at this jamming transition, what we have done, we have developed some kind of percolation. This seems a session for percolation. Some kind of percolation we call random first order percolation transition, because this type of percolation that I'm going to show you now is a percolation which describes the critical point of the random first order transition. And this percolation is essentially percolation done with the clusters which corresponds to the cooperative rearranging regions, which are the droplets of random first order transition. What are these clusters? These are clusters which are compact and have a fractal dimension d, capital D equals to D, the dimension. And the linear dimension of this cluster diverges with an exponent rho j minus rho j minus rho to the minus nu, where nu is 2 over D, the exponent of the random first order transition. So the percolation order parameter jumps discontinuously, just like you have in a jamming transition, discontinuously from 0 to 1, but this percolation exponent is a sort of mixed order percolation exponent, because the percolation exponent jumps discontinuously, but the other critical exponent, already we have seen that psi diverges with an exponent nu, and the mean cluster size exponent, which is given by 2 capital D, the fractal dimension minus D times nu, if you insert nu and the capital D, which is equals to D, the fractal dimension, then you get gamma equals 2, and alpha, the cluster number exponent, equals to 0. So in conclusion, we get the exponent alpha equals 0, beta equals 0, gamma equals 2, and nu equals 2 over D. So this exponent, as you see, alpha, beta, and gamma, satisfy the scaling relation, and these exponents are independent on dimensionality, a property which we have seen to happens also in the jamming transition. So if this all this is correct, it predicts a kind of percolation problem which describes the jamming transition, which has the same property of that we find in the jamming transition, namely that the critical exponent are independent on dimensionality. And what is interesting is that this exponent also satisfies the hyperscaling relation in every dimension. So there is never a dimension where this hyperscaling is not satisfied, which suggests that the upper critical dimension is not D equals 2, but the opposite is D equals infinity, because you never break this hyperscaling relation. So this exponent, this percolation problem, which again applies, if you like, to the random first order transition. Once we have shown that random first order transition, or we have suggested, if you like, coincide with the jamming transition, this percolation applies also to the jamming. And what I'm trying to say that this kind of percolation has the nice feature and property that we find in the geometric transition. So, in conclusion, so what we will suggest is that for hard sphere in finite dimension, the ideal glass transition of the RFEOT theory coincides with the ideal geometric transition which occurs at infinite pressure at the end of an equilibrium line. So we have been able to describe this glass geometric critical point as random first-order percolation transition. And this percolation transition is characterized by a mixed-order transition with exponents which are independent of dimensionality, except the critical length nu, which instead depends on dimensionality. Nu equals 2 over d. And as you have seen, these exponents satisfy both scaling and hyperscaling in any dimension, showing that there is no upper critical dimensionality. Thank you very much.